Okay, so the first set of lessons we talked about evaluating limits graphically. And so now I want to talk about evaluating limits algebraically. And there's a couple different things that we're going to talk about here. So just kind of stick with me, do the things I'm telling you to do, and we will get through this very nicely. So step one is when you see a limit, like the limit is x approaches 4 of x squared minus 10x plus 5. When you see this limit thing, you need to understand that the limit as x approaches 4 is not the same as f of 4. These do not mean the same thing. Now, the values may be equal, but the meaning behind them is not. So when we do some of these, I'm going to tell you to like plug in 4, plug in 2. I'm not telling you that because that's always going to get you the limit, but that's always where you want to start. Because the reason limits exist is because sometimes functions don't, or the function does exist, but it does different things. So what we do is we look at the limit to figure out, well, if the function existed and it was nice, where would it be headed? And the easiest way to start figuring that out is to try to just evaluate it outright. So anytime I tell you just plug in the number, I'm telling you try that, see what happens, and then decide what to do next, okay? So substitution. Sometimes we can evaluate the limit of an expression by direct substitution. We can only do this when we've considered the fact that a discontinuity may exist. Once we're sure that there is no discontinuity, then we can proceed, okay? This is what I was talking about. Step one of evaluating any limit should be to substitute and let the result guide you, okay? So, x approaches 4 of a parabola. Well, a parabola is a polynomial. Every polynomial has a domain of all real numbers, and every polynomial is continuous and differentiable, but that comes up later. So anytime you have just a polynomial, you can just plug it in. The limit as x approaches 4 is going to be the same as what you get when you just plug in 4. So I have 16 minus 40 plus 5, which is going to be, let's see, 16 and 5 is 21, minus 40 is negative 19. So there's the value of your limit. Next limit over here, and by the way, I'm sorry about these boxes. I don't know why they show up. It's just my computer being bizarre. Next one, x approaches 0. Well, this has discontinuities. When I have cosine x on the bottom, anytime cosine equals 0, this function doesn't exist. However, the limit in question, if I plug 0 in for cosine, cosine of 0 is 1. So this is not one of the discontinuities that happens to exist. So I'm okay just to plug in the value. So as x approaches 0, I have ln e to the 5th. And on the bottom, I have cosine 0. So ln of e to the 5th is going to be 5. Cosine of 0 is 1. So that limit equals 5. All right. And then last but not least, 2. Putting a 2 on the bottom doesn't change anything. Putting a 2 on top, I still have a real answer. So I have the square root of 9 on top when I plug in 2. And when I plug in 2 on the bottom, I have the absolute value of 9. So this is going to be 1/3. Okay? So substitution, one way of evaluating limits. However, that's not the real reason limits exist, because if I could just substitute, I probably wouldn't be asking for the limit anyway. So here's where things get different. One-sided substitution. If you want to evaluate a one-sided limit, you're going to use your noggin. Okay, we're going to think about what happens if we pick a value really close to the constant in question. So let's say I want the limit as x approaches 3 from the right for this. Now first, let's try to do direct substitution. So step one is, what would happen if you did direct substitution? Well, if I do direct substitution, I'm going to write in yellow. I would have 3 minus 3 over the absolute value of 3 minus 3, which is 0 over 0. Okay? That is undefined. When it comes to 0 divided by 0, what happens is this. The bottom 0 is the right bower of all rules. Anytime you have anything and there's a 0 on the bottom, it doesn't matter what else is happening in that problem. The 0 on the bottom makes the entire thing undefined. Okay, doesn't matter what else happens, 0 on the bottom makes the whole thing undefined. So when I look at this, I realize, well, I have one of those undefined situations. Direct substitution does not work. So what I'm going to do now is I'm going to use my head. So I'm going to say, all right, coming at 3 from the right, we'd be a value of like 3.001. So I have 3.001 minus 3, and then 3 minus 3.001. Well, on top, that's going to give me 0.001, and on the bottom, it's going to give me 0.001, which heads to 1. Now we need to think about that for a minute. Is that always going to happen? Is the top always going to equal the bottom when I come at 3 from the right? Well, yeah, because the difference up here is equal to the difference down there. The difference up here is always positive. That's always positive. So a positive number divided by itself is going to be 1. So that is the value of that limit. Now when I look about this, I've got the limit as x approaches negative 8 from the right. Okay, so to the right of negative 8 is going to be like negative 7.999. So first let me try direct substitution here. So if I do direct substitution on this one, if I plug in negative 8 here, I'm going to get the square root of negative 16 plus 5. And on the bottom, I'm going to have negative 8 over the absolute value of negative 8. Okay, well up here, this just gives me 5. And down here, that gives me negative 1. So by direct substitution, I end up with negative 5. Well, okay, now let's try to deal with the fact that it was asked as a sided limit. So if I pick like negative 7.99 times 2 plus 16 square rooted over negative 7.99 over its absolute value, let's see if I end up with the same thing. So up here, negative 7.99 times 2 plus 16, this is going to be a number really close to 0 and positive. So technically, yeah, this is going to be greater than 0, but it's going to be like 5 plus the square root of like 0.001 or something, which is really going to be basically 5. And then down on the bottom here, I have negative 7.99 divided by positive 7.99, which is going to be negative 1 again. I still get negative 5. And if I really think about this, the reason we ask this as a right-sided limit is because if I take negative 8 from the left, this limit doesn't exist because that would be like negative 8.01, which is going to give me a negative under this radical, and I wouldn't be able to evaluate it. So this is a case where the only reason the sided limit is even asked is because if I come from the other side, the limit doesn't exist. Okay. All right, and then last but not least over here, the limit as x approaches 2 from the right for a piecewise function. Well, what would happen if I just plug in 2? Well, I can't because this doesn't exist at 2. So the only way for me to evaluate this is to talk about a sided limit. So if I approach 2 from the right, that means values bigger than 2, which means come up here. And if I want to evaluate 2 from the right, I'm just going to plug 2 in to that side, and that gets me the limit. I don't have to pick a number close to 2 because technically I'm kind of doing that already. So this is like 2.00000000001 plus 1, which is essentially 3. Okay. Next, we have, let's see, substitute, simplify to remove the discontinuity, and substitute again. Okay, what does that mean? Sometimes direct substitution results in an indeterminate form 0 over 0. When this happens, then the function must have a discontinuity at the point because I've got a 0 on the bottom. However, it's likely that we can remove the discontinuity through simplification. So, long story short, what this paragraph says is it says if you do direct substitution and get 0 over 0, that's a really good indication that maybe you can cancel those zeros out and evaluate the limit anyway. So, if I look at this one, the limit as x approaches 4. If I plug 4 in, I have 16 minus 16 over 16 minus 8, which is 0 over 0. When I have a 0 over 0, it gives me a chance to say, you know what, I bet something cancels. So then you're going to say, well, if something cancels, that means I can simplify. So this limit, as x approaches 4, is rewritten as 4 minus x, 4 plus x, over x minus 4, x plus 2. This limit right here is equal to the limit as x approaches 4 of negative 4 plus x over x plus 2. Does this have a discontinuity at 4? No, it does not. So now I can just plug in 4, and I end up with negative 8 over 6, which is negative 4/3. Now, quick thing. The limit here is equal to the limit there. However, the function here does not equal the function here. These functions are different. How are they different? Well, the difference is if you cancel something out like this, that means this function had a hole at that discontinuity. When we cancel it, it simplifies down to this, which really means these two things are not really equal. They're equal 99.9% of the time. However, this one has a hole at 4, and that one does not. Okay, that's the difference. So the functions are not equal. However, the limits are equal, and that's kind of an important distinction. All right, so what about this one? Well, if I plug in 9, I have 3 minus 3 over 9 minus 9, which is 0 over 0, which means I can probably cancel something. Except I can't really factor this so well. So instead what we're going to do is when we have a radical, you want to think about rationalizing the numerator or the denominator. Now, as far as how do you show work in calculus, if you just want to jot stuff down, you don't have to show me the same example, the same equation over and over and over again. You do not have to do that. So what I'm okay with is you just kind of writing something like this and saying I've got that, and then I'm going to multiply this by the square root of x plus 3, multiplied by the conjugate to rationalize the numerator. And then if I look at this and I FOIL the top, I have x minus 9 over x minus 9, square root of x plus 3. These would cancel. So now what I'm really doing is I'm evaluating the limit as x approaches 9 of 1 over the square root of x plus 3, which is going to give me 1/6. Now notice I didn't do like what I did over here where I wrote one limit and said equal to another limit and then gave an answer. If you just want to kind of do some work off to the side and then reevaluate over here, that's fine. Okay? The issue is when you start writing a big string of equations with equal signs, you may end up with what's called a linkage error, because if you link things together that aren't equal, technically that's where you make a mistake. What we did here to avoid that is I didn't put any equal signs in anything. I just kind of said, hey, I'm doing some work. This is the work I did behind the scenes to get this as a final answer. That is totally okay. All right. And then last but not least here, we're going to look at this guy. This is a big old complex fraction. If I plug in 1, I have 1 minus 1 over 1 minus 1, which is 0 over 0. So I'm going to simplify the complex fraction. So I'm going to take 1 minus 1 over x and 1 over x squared minus 1. And the way I like to handle complex fractions is I multiply the numerator and the denominator by the least common denominator for everything, which would be x squared. So when I distribute this x squared, I end up with x squared minus x, and on the bottom I end up with 1 minus x squared, and then that is equal to x times x minus 1 over 1 minus x, 1 plus x. I'm sorry for the squishiness of this. Then these guys cancel and I leave a negative sign behind. I'm sorry, I'm just going to move it down here. It stays blue, so that'll help. So now what I'm really doing is I'm evaluating the limit as x approaches 1 of negative x over 1 plus x, which is going to give me negative 1 over 2. And there is my limit. If these last three expressions were all graphed as functions, what would the graphs look like at the point of discontinuity? That's what I was discussing when I was writing in purple right here. They would have holes. The original expression has a hole at the discontinuity, and the simplified expression does not have the hole. It's filled in. Okay? All right. And then last but not least on here, we're going to talk about creating continuous functions. So remember, in order for a function to be continuous, both one-sided limits have to approach the same value, and the function must equal that value as well. So let's say I want to look at this thing at 2, and I want it to be continuous. Well, this is a piecewise function. Right now, it might look something like this, or it might look something like this, and I don't know what it looks like. Okay, so basically right now any piecewise function might be broken. If I want it to be continuous, what I really want to do with it is this. I want to take this, I gotta show you what to do, there we go. I want to take this, and instead of having them broken, I want to take them and I want to shift, why didn't this work? There we go. I want to shift it so that the line and the point come down to fill in the other thing. All right, well, how do I do that? I say, well, if I want the graphs to touch, that means the equations, or expressions in this case, have to be equal. I need ax minus 4 to equal x squared. But I don't need these things to be equal all the time. I just need them to be equal where it's broken, and it's broken at 2. So I need 2a minus 4 to equal 2 squared. So I need 2a to equal 8, so a has to be 4. That would make them line up. So you set the expressions equal, plug in where it's broken, and then solve for the values you need. All right, find a and b so that g of x is continuous. So this has 3 different pieces. When x is less than 3, I've got like some kind of, that's not a parabola, I've got like some kind of parabola, and then that's going to have a hole at the end of it. And then at 3, I've got 6, and then above 3, I've got like another hole in a line. So this potentially could look something like that. Well, I want these 3 things to line up. So if I want these 3 things to line up, I need 2x squared minus ax plus b to equal 6. And I need ax plus b to equal 6. But I don't need them to equal 6 all the time. I just need them to equal 6 at 3. So I need, when I plug in 3 here, 18 minus 3a plus b needs to equal 6. And when I plug in 3 here, I need 3a plus b to equal 6. Well, that's 2 equations. That's okay. It's 2 equations and 2 unknowns. So if I have 2 equations and 2 unknowns, I'm going to take this and say, well, this is just a system. I'm going to add the 2 equations together. These guys cancel. I've got 18 plus 2b equals 12. And then if I subtract 18, that means 2b equals what? Negative 6. So then b is a negative 3. And since 3a plus b has to equal 6, 3a minus 3 equals 6. So a is going to have to be 3. So if a equals 3 and b equals negative 3, that takes these 3 things, and very nicely for us, we'll shift them down so that they all fit together. Oops. Well, anyways, they're supposed to shift together. I don't know what's going on with my computer right now. But anyways, it's going to bring them all together. A equals 3, b equals negative 3. All right, and as promised, we're going to have a dumb joke. So my dumb joke for today is an elephant joke. So an elephant is climbing up a tree, and he sees a squirrel above him, and the squirrel goes, dude, what are you doing? And the elephant says, I'm climbing up to eat some pears. And the squirrel says, buddy, you can't eat pears up here. This is an apple tree. And the elephant says, that's okay. I brought my own pears. I know it's dumb, but if you had the voices, it's actually much funnier. All right, I hope you guys have a good day.